All right, welcome back to week 5. We're going to continue with our work on U substitution. So U substitution, what is it good for? Well, basically it's used to undo the chain rule. And we use the chain rule when we were doing the derivative of a composite function. Now if you recognize, there's certain patterns that you can recognize that'll help you know that U substitution is a good tool. All right, and that first, here's an example of what I mean. If I wanted to find the indefinite integral of 2x times the square root x squared plus 2 dx, so that's going to be one that we're going to do, and then we're going to compare that to if I wanted to find the indefinite integral of x times the square root of 2x minus 1. All right, one pattern that we noticed last week was a good hint that you're going to use U substitution is when the expression that you set your U equal to, so for example, in this one, we said we would let U equal x squared plus 2. Now, what I notice is when I take the derivative of this, and I do the derivative of this side, so that would be 2x plus 0 dx, and I divide both sides by 2x, I get du over 2x. Now, what you notice is, hey, when I do the derivative here, that term is also a factor of the integrand. So what's going to happen is when I substitute these in, that 2x is going to cancel out, and I won't have mixed variables. I won't have a u in there along with an x. All right. Now, so let's go ahead and do that, see how this shakes out here. So I'm going to substitute. I got, that's 2x, and then here that would be u to the 1/2. And then for the dx, I'm going to put in du divided by 2x. All right, and then we can see that the 2x's cancel out, so I just have u's. I don't want to have u's and x's. I need to have just one variable. All right, so now I would integrate u to the 1/2 du, and that would be u to the 3/2 over 3/2 plus some constant c. So when I simplify that, I'd have 2/3 u to the 3/2 plus my constant of integration. Okay, and now I substitute back in my value of u. And there's my antiderivative. All right. Well, what happens when you go to try to use U substitution and this extra or this factor here doesn't cancel out? What do? All right, so that's what I'm going to show you over here. So on this one, if we were going to, this is dx. Okay, so here I would let u equal 2x minus 1. Okay, I'm going to do the derivative. Now, I wrote it like this last week. Du dx equals, this would just be 2, and then we multiply both sides by dx, and then we divide it by 2. Well, all I did over here when I did that this week was I just wrote, okay, what, du, and then I did the derivative of the right side, which is 2 dx, and then I divided both sides by 2. It's the same thing. All right. Now, what happens when we do our substitution here, we have x. Now I've got u to the 1/2, and then I got du over 2. And the problem is there's nothing to cancel out that x. So you can't integrate it when you've got these two different variables in it. All right, so what do? Well, what we have to do is take this x and write it in terms of u. Right? So to deal with this, since it doesn't cancel, we're going to have to rewrite, okay, in terms of u. So I'm going to take this equation here, u equals 2x minus 1, and solve it for x. So I'd have u plus 1 equals 2x, and then u plus 1 divided by 2 equals x. Right? Now I can rewrite this. I'm going to take out that x and replace it with this. So now I have u plus 1 divided by 2 times u to the 1/2 du over 2. And now we're going to integrate this. So that's how you deal with it when it doesn't work out, that it cancels like it did on the first example. All right, so let's see how it goes from here. Okay, so the first thing to recognize is this is really 1/2 times this quantity, and this is 1/2. So 1/2 times 1/2 would be 1/4. So I can pull that out in front of the integral. And now I'm left with u plus 1 times u to the 1/2 du. Right, next step is I'm going to distribute through the u to the 1/2 power. So when I'm multiplying here, I'm going to add these exponents, so that's a 1. So 1 plus 1/2 is 3/2 plus u to the 1/2 times 1 du. And now I can do the integrals of those. Okay, so 1/4. All right, add 1 to the exponent, so 2 over 2 makes that 5 over 2. Plus, add 1 to this exponent, that gives me 3 over 2. Plus some constant. And now what we would do is we'd clean this up, simplify it, and then substitute the u back in. All right, so here's the simplification. So I just rewrote my fractions, then I distributed the 1/4 through, and now I'm going to reduce these and substitute in my value of u. So here I would have 1/10 times 2x minus 1 to the 5/2 plus 1/6 2x minus 1 to the 3/2 plus c. And there's your integral. So it's a little bit more work, but you can still deal with it. You can still use U substitution when you have an additional factor in your integrand that doesn't get canceled out by the derivative. All right, now in today's lesson, we're going to do U substitution when we've got to integrate the product of two functions, and some of those functions will be our special functions like logs and the natural base e, etc. All right, so our first one up is U substitution involving an e, the natural base. So up here I summarized some tips for when you're going to use U. What we showed in the last example was when you have a function what you're going to do is set your U equal to a function whose derivative is also in the integrand. That's what happened right here. Okay. All right. The inner function of a composition, function raised to the highest power, a function that's in the denominator. Okay, so in this case, if we look at this for a second, if I let that equal U, then when I do the derivative, it's going to cancel out that 2x. So in this case, I'm going to let U equal x squared. So the du, if I do the derivative of that, it's 2x dx. Solve that for dx, and I get 2x. Okay, now we can go ahead and do our substitution. Integral of 2x e to the u, and then for dx, I'm going to substitute in du over 2x, and nicely, these cancel. So now I'm just integrating e to the u, and we know that its antiderivative is itself. So this would be e to the u plus some constant c. All right, now substitute in our value of u, and there's our antiderivative, or our integral. Okay, when we know a point on the original equation, right, we can substitute in and we can get the value of c. That's what this is telling us here. All right, so this is the point on the original function, and it would be the point 0, 2. So the 0 is going to go in for the x, and the 2 is our y value, or you can think of it as also f of x. All right, so my antiderivative is okay, so for this, I plug in 2. For x, I put in a 0. And now I can solve for c. So any base to the 0 power is 1. So I know that c is equal to 2 minus 1, or 1. Okay, now I can write my antiderivative as e to the x squared plus 1. Okay, now we've got an E and we've got a trig ratio in there. So U substitution with trig functions. All right, over here, I pasted our rules for integrating trig. So the antiderivative of cosine is sine, and the antiderivative of sine is negative cosine. So what I notice here is that if I let u equal sine, when I do the when I do the derivative of it, I'm going to get negative cosine, and I'll be able to cancel this part out. Okay, so to integrate that, we're going to let our u equal sine x. Now I'm going to do the derivative of the left side. Okay, the derivative of, now the derivative, not the integral, but our derivative of sine. Okay, so our derivative of sine is equal to cosine, not the antiderivative, the derivative. Now, okay, now I can rewrite my integral. And now, let those cancel. And I should have put that, I should have substituted in my u. I didn't, so just e to the u du. And now the integral of e to the u is itself, so this would equal e to the u plus some constant c. And now I can substitute back in my value of u. So this would be sine x plus c. Now we're going to use, okay, so to evaluate this integral, there's our lower and our upper bounds. So it's simply a matter of substituting those in. We don't have to worry about c because we have the bounds here. So this is simply going to become e to the sine pi over 2 minus e to the sine at 0. Okay, so on our unit circle, okay, at 0 radians, our point on our unit circle is 1, 0. This is the cosine of 0. And that is the sine of 0. So this becomes a 1, or excuse me, a 0. And then at pi over 2, our unit circle has the coordinates 0, 1. So our sine at pi over 2, this part is equal to 1. So I just end up with e to the first minus e to the 0, which is just e. Minus 1. E to the 0 is minus 1. Sorry about that. Okay, let's move on here. All right, number 4, we got finding the antiderivative of some more trig functions. So what I notice here is that if I do the derivative, if I let u equal cosine, when I do its derivative, I'm going to get negative sign, and I'll be able to cancel out that sign. All right, cosine to the third x, that is the same as cosine x cubed. So I'm going to let u equal cosine x. Do my derivative. The derivative of cosine is negative sine. Okay, now I'm going to do my substitution. All right, and nice. So I'm left with a negative 1. That's a constant. I can pull that out front. Substitute back in my value. And there is my antiderivative. All right, number 5. Now we've got U substitution, and we've got some natural logs in there. So U substitution with natural logs. All right, so here we have a definite integral. So what we're going to do is we're going to get a value for this. We'll evaluate this first. And then once we have that done, then we're going to set that, whatever we get for that integral, we're going to make it equal to the natural log of k. So whatever we get for that value is going to end up going right here, and then we can figure out what k is. All right, so for our u substitution here, I'm going to let u equal this denominator, because when I do the derivative of this denominator, it's going to be 2, and that'll cancel out this 2. So let's go through and do that. So I would have, let's see, u is going to equal 2x plus 5 So here I've got 2, okay, u this is 1 over u, du. Okay, now I'm going to integrate that. So our integral of 1 over u. All right, so earlier in your notes, you had, when you have 1 over x, its derivative is the natural log of the absolute value of whatever this argument is. So this here would be the natural log of u, and then I'm going to evaluate that from 0 to 5. Okay. So I'm going to substitute in, before I do that, I should substitute, that should be an absolute value. So now I'm going to substitute in my U value. Okay, so I'm going to put 5 in. So that would give me the natural log of 2 times 5, 10, plus 5, 15, minus the natural log of 2 times 0, 0, plus 5, 5. All right, and if you remember your natural log rules, this is the same as the quotient 15 over 5, which equals the natural log of 3. Now I can take that value and put it right here, and that tells me that k is going to equal 3. K equals 3. All right, if you look at our rules for derivatives, we're looking for a function whose derivative is tangent. So there's not a direct function in our rules that has a derivative that's tangent. Now we know the derivative of tangent is secant squared, but we need to know when we take the derivative of whatever this is, we end up with tangent. So a strategy in this case that's effective is to rewrite tangent as sine over cosine. In this case, d theta. So in this case, I'm going to let my u equal the cosine theta, because when I do the derivative of cosine, it's going to equal negative sine, and I can cancel out that sine on the top. Okay, so we're going to let u equal cosine. So I'm going to do the derivative both sides. And then this is going to, the derivative of cosine is negative sine. And then I'm going to divide by negative sine theta. Okay, so I can rewrite my integral now. Cancel, I'm left with a negative, so I'll pull that out front. Okay, from the last example, I know that this is equal to the natural log of the absolute value of u plus some constant. And now substitute back my value of u, and there is my antiderivative. All right, guys. Well, we'll see you next time. Have a good day. Take care. U substitution rules.